In this video we're going to look at dimensional analysis. For us, dimensional analysis primarily means analyzing the dimensional consistency of an equation. It can be incredibly useful, it can save a lot of time, and it's also just good practice generally. So by analyzing dimensional consistency of an equation, I mean you look at the dimensions, like length, mass, or time, on each side of the equation, and they need to be equal in the same type and order of magnitude. So by type I mean like length and magnitude, or order of magnitude, the power. So if it's an equation that's describing area, then it should be length squared on one side and length squared on the other side, or volume cubed. That's the primary way we'll use dimensional analysis in our class this year. It also can be used for building an equation for testing, or building a model that you intend to test, such as through experimentation. So some example might be if I had a question like, how does fall time vary with the height with which I release a dropped object? Well, I could build up an equation that I think describes that, and then use dimensional analysis to help me make sure that it's at least dimensionally consistent. It doesn't necessarily mean it's going to be true. Okay, so we'll do a couple quick examples here, and primarily for dimensional consistency in this class, we're looking at length, mass, and time, our first three major dimensions, and we abbreviate them first of all by with a capital letter for L, for instance, for length, with brackets around it. Brackets show us we're talking about the dimension. Capital M for mass, capital T for time, all in brackets. So take the equation such as c equal 2 pi r. Circumference, we know that circumference is some length dimension, and that's underlined in orange. Radius, r, is some length dimension, I've underlined in orange. But 2 pi has no units, 2 is just a number, and pi is also just a number. It's a ratio of two other physical values, so these don't represent any physical dimensions. So when we do our dimensional analysis, those things that don't have physical dimensionality drop out from the equation. They're just constants. So the radius we said is the length, circumference is the length, so we have big L on each side, and so if we're analyzing the dimensional consistency, it's L to the first power equals L to the first power, and so that is dimensionally consistent. Another example real quick, counterexample rather, say I said the volume of a sphere is equal to 4/3 pi r to the fourth power. Well, I look at my parts of the equation that should have dimensionality, and that's the volume and my radius, and I know a volume should be some length dimension cubed. My 4/3 pi drop out, and on the right side I have r, which is a length value to the fourth, and I notice that I have the same dimensions, length and length, so does that mean it's dimensionally consistent? No, because it's two different powers on the left and the right side. So both the type and the power need to be the same for the equation to be dimensionally consistent. We'll look at a couple kind of problems that can help drive this home, I think. First, the radius of a circle described in any triangle whose sides are A, B, and C is given by the following equation, in which S is an abbreviation for, open parentheses, A plus B plus C, close parentheses, divided by 2. Check this formula for dimensional consistency. So I'll pull out some stuff from my question that I know. I know S is equal to what it says it is, A plus B plus C over 2. I also see in my equation, or from my problem rather, that A, B, and C are described as sides of a triangle, and a side is a length to the first power. So, secondly, I know that A is a length dimension, B is a length dimension, and C is a length dimension. And those go in the numerator of that, what S is equal to. So I can rewrite what S is equal to right there. You can see it's 3 length values over 2. Well, what do we do with this? We know that 2 is dimensionless, and we need to ask what happens when we add lengths or subtract lengths or any other dimensions. We get the same type of dimension. It's only going to change if I have like L times L, then I'll get L squared for area. Or if I multiply by another dimension of length, I'll get L cubed for volume. But if I add a length to another length, I just still have length to the first power. So S is equal to just, it has the dimension of one length. I can substitute this back into my equation over there on the left, and that makes things a little easier because of S minus A, which is length minus length, times S minus B, length minus length, times S minus C, which is a length minus length. All is going to be divided by a length dimension, and so as you can see, like we just said, length, or any dimension plus or minus the same dimension, is just going to be the same dimension again, just a different magnitude of it. So I have length times length times length, all divided by one magnitude of length, and the square root of that. So I end up with L cubed over L, which becomes L squared, and the square root of which is L. So we have L to the first power, and it dimensionally checks out. So the question is this equation dimensionally consistent? Yes. Is this equation correct? I don't know. Maybe. Just because it's dimensionally consistent does not necessarily mean that the equation is correct. So dimensional analysis is extremely helpful for letting us know if an equation is dimensionally sound, meaning does it make sense at least physically in the dimensions it's representing with the variables and how they're being combined. That's very helpful to know, because if an equation is not dimensionally consistent, we do that analysis before we try using the equation. We do that analysis and it shows us that it is not dimensionally consistent, then we know it's garbage already and we don't want to keep going using that. Or we know maybe if we've been deriving something and we check it for dimensional consistency and it's not consistent, then we can go back and see maybe we made a mathematical error somewhere in deriving our equation. So dimensional analysis helps us see whether it's consistent, but just because it is consistent does not necessarily mean it's correct. However, if it is dimensionally inconsistent, meaning the dimensions don't match up, then we know it is not physically valid, and it cannot be the right equation. Let's look at another problem real quick, a slightly different one. This one's going to use an actual physical equation. Previously, that equation about circle inscribed in a triangle or triangles inscribed in a circle, we would have to do a geometric proof to show if that equation was in fact correct. This one over here is asking about the period of a simple pendulum, so that's what the capital T is. Notice it has no brackets around that capital T, and that's the variable for the period, or the time that it takes for a pendulum or an oscillator to complete one back and forth movement. So if I put my brackets around a T, that's the only time I'm talking about my time dimension. So this equation T equals 2 pi times the square root of L. L is the length of the pendulum, divided by A sub g. That's the acceleration due to gravity near the surface of the Earth. And the problem tells us that acceleration due to gravity has the units of length divided by time squared. Or I would really correct that and say it has the dimensions of length divided by time squared. And its units would be something like meters divided by second squared. Anyway, check this equation for dimensional consistency. Let's go. I'm going to highlight some things that are important in my equation, or in my question rather. I know that the period t, the length L, and the acceleration ag, or just g, are physical things and have dimensionality rather. 2 pi, like we said before, is just a number and a ratio. It drops out of my analysis, so I have big T in brackets now for time, that's the period, equals the square root of bracketed L for the length of the pendulum, divided by what the equation or the problem told us, length over time units squared, or length dimension divided by time dimension squared for little g down there in the denominator under the radical. That's what those correspond to. I've substituted in what my dimensions are. Now I'm just going to kind of clean up the equation so I can analyze it. I don't really like fractions inside fractions, so I pull out that denominator. I have to flip it in order that I can multiply it by my numerator. So I have under the radical length dimension over 1 times time dimension squared divided by length dimension. You see those lengths cancel out, and I get, ta-da, the square root of time dimension squared, which is time dimension to the first power. Also realize or remember that we can write our radicals as to the 1/2 power if it's a square root symbol, and that can often be helpful for rewriting these. There we go. I have 1 time dimension to 1 time dimension, and I ask myself, is this equation dimensionally consistent? Is it? Yes, it's the same type of dimension and the same order of magnitude. T to the first power, t to the first power. Is this equation correct? Well, you need to design an experiment if you would want to find this out, or we could do like we will when we encounter dynamics and simple harmonic motion. We can look at the derivation of a formula or an equation that describes this period, and that equation can be sound, and then we'll go to the lab and test it out and see how physically reasonable it is during our experimentation. So again, same kind of question as last time. Is it dimensionally consistent? Yes. Is it true or correct? We don't necessarily know that until we actually derive a proof. And in our case, since this is describing a physical thing, we should go test that in the lab with an experiment. Often, on the right side now, I do dimensional analysis with units, so you can call that unit analysis or what have you. That can just be a little quicker, you're not writing all the brackets, and just to see what that looks like, capital T over there is our period again, so seconds are the units, 2 pi falls out, length is meters divided by meters per second squared for length over t squared. Same sort of process as I just did, I'm just using the unit symbols. So I have seconds equals seconds, so again it dimensionally checks out. Those are all for our examples. A couple things to keep in mind. This is incredibly useful in the AP exam. It's incredibly useful when you're solving a problem that requires you to manipulate a literal equation, such as the period equation over here. And say you want to solve t equals 2 pi times the square root of L over ag, and you're asked to solve for L or something. Well, you can go ahead and solve for L, and then whatever your result is, L equals whatever that is, you can check that final equation you've come up with for dimensional consistency. And if it's dimensionally consistent, then you know that you at least have some support in your final answer. Because if it's not dimensionally consistent, you would know you messed up somewhere in manipulating that equation. If it is dimensionally consistent, you know you at least got the dimensions right, and that's good. It's still possible that you could have made another mistake, but dimensional analysis is a quick way to check that. Often on the AP exam there are a lot of questions, or there's usually like one maybe in the lab analysis part where it'll say some student found on the internet or derived an equation to describe the angular velocity of this thing. There was a similar question to this on the pretest that we took. And the AP exam will ask, show, without deriving a whole equation, show why this equation the student came up with doesn't make any sense or why it won't work. And one way to analyze that quickly and give a good reason for why it doesn't work is to do a dimensional analysis of that equation some student picked up. And if it's not dimensionally consistent, you can stop right there and say, hey, look, College Board, it's not dimensionally consistent, so this equation is garbage, and you move on to the next question. That's a great skill to have. It's really good at saving you time when you're deriving your own equations or manipulating them, like I just spoke about on the period equation. It will be useful on the AP exam as well.